I'm Bill Hammack.
And I'm Don DeCoste.
And this is a commentary track to Lecture 4 of Michael Faraday's The Chemical History of a Candle. We created this with Alex Black, and this commentary track is to help you understand the lecture better.
So at this point in the first three lectures, Faraday has really talked a lot about the candle, how it works, the products of the candle. And at this point, he's going to start broadening out a little bit more. We're going to get into a discussion a lot of the atmosphere, and that's going to lead us into the next lecture about comparing the combustion of a candle to human respiration.
Now, in the last lecture, he pointed out what you see here is that a flame will burn more brightly in pure oxygen. In fact, he left us with just a little bit of a mystery that if things burn in oxygen, why doesn't our world just burn up and disappear? And he's going to tackle that here. He's going to explain that air has something called nitrogen in it and explain, even though it's inert, why it's so important.
And what's nice about the way that he does this, he doesn't just come out and say, oh, by the way, there's nitrogen in the air as well. He actually does some experimentation to show there's something else besides oxygen.
And I think it's a good reminder to us that we need to let our students do inquiry, that when we give them experiments to do, that we don't tell them the outcome, that instead let them do some discovery.
And, this is one of the places where we changed what Faraday did. Faraday had mixed air with nitrous oxide, which was somewhat hard to come by for us, also very dangerous. And so we decided to do a different kind of classic demonstration. And this is the so-called blue bottle demonstration. A lot of teachers may be familiar with this. We often use this as kind of an inquiry-based lab. Use this for kinetics as well. In this case, we have, as you can see, potassium hydroxide, glucose, and methylene blue indicator. And when it mixes with oxygen, it turns this blue color, which fades over time. And what students can do as far as inquiry goes is, as they shake it, turns blue, fades, they shake it again, they notice that it doesn't turn blue as quickly, doesn't stay blue as long, eventually learning that, or trying to discover that perhaps it is actually reacting with the oxygen that's in the air.
And I think it's useful to point out here that this is essentially another kind of analytical chemistry test. What he has developed, or what we've developed here, showing you rather, is a concentration meter. That business of the time you wait until it fades, gives you a feel for the concentration of the oxygen that's in there.
So we didn't give enough time for the flask on the left, the one with pure oxygen above it, to fade to colorless, which it will over time. The other thing is we want to listen to the way Faraday introduces nitrogen without saying the word nitrogen.
Because there is in air, besides oxygen, something else present. The solution left something untouched. There is, in fact, a gas in air which the solution cannot touch, and this gas is not oxygen, and yet is part of the atmosphere. I love that phrase, it left something untouched, and that just, shows why we kept the original language. And I also think it's just really instructive, as you hinted at, that he didn't mention nitrogen right away. He showed us an observation first, and now he's going to show us the implications of that observation. And Faraday's going to point out that nitrogen is inert, but that it really has, an important function in our world.
And one of the things that Bill and I both like about Faraday is his positiveness about everything. In the first lecture, he mentioned the beauty of a candle, looking at the cup, something very simple that we've seen before, but it's beautiful. We then look at beautiful candles that aren't very useful, and he finds beauty in that too. The beauty is that we learn something about how candles work. And it would be easy enough to be negative about nitrogen, which Faraday is going to disabuse us of. Now let's listen to Faraday introducing the pessimistic view of nitrogen.
And you might say, it is nothing. It is not worth chemical attention. What does it do in the air? Then come our beautiful and fine results shown us by an observant philosophy. And so Faraday, the great showman, constructs this whole alternate world of what would happen. I mean, it kind of reminds me a little bit of like Ice Nine, which was in Kurt Vonnegut's novel
Cat's
Cradle. And he's going to show us all the terrible things that can happen. That grates will disappear, as you see here. What else is going to happen?
The trains.
Yeah, that's coming up, right? That the trains would just be destroyed. So this is an engine here, and if you think about it, his audience would have had intimate familiarity with trains. This would be something that would be astonishing to them to disappear. And then he links it to lightning, if I remember coming up. Is that right?
Yeah, he talks about that the lightning is the only thing that can affect the nitrogen, that it's that inert. And you mentioned that he's a showman, and so he normally would show us these demonstrations, but it also shows shows that he's a really good storyteller as well, because obviously, we can show these graphics of the great burning and we can show the train. He wasn't able to do that, but he was able to kind of paint a very vivid picture.
Yeah, and here's our lightning. And if we didn't have nitrogen, the what would happen? The lightning would just ignite the atmosphere.
That's right.
Right. And so there's this apocalyptic scenario that he is spelling out here, which I think is just fascinating.
And all of these too, the fireplace, the nitrogen, or the lightning. The audience was familiar with all of this, and so he was able to bring that to them as well.
So he concludes this discussion on nitrogen with emphasizing why the pessimistic view is not the right one, but why you should have an optimistic view of the effects of nitrogen in the atmosphere. And it's very nicely done. It requires all that quantity of nitrogen to reduce the oxygen down so as to be able to supply the candle properly with fuel, so as to supply us with an atmosphere which our lungs can healthily and safely breathe. For it is just as important to make the oxygen right for us to breathe as it is to make the atmosphere right for the burning of the fire and the candle.
And notice what he did there right at the end. He said it's just as important to make oxygen right for us to breathe as it is to make the atmosphere right for the burning of the candle. And this is where he's going in Lecture 5, to couple human respiration with the combustion of the candle.
So now he's showing us that gases have weight, that air and other gases consist of matter. And he's going to spend the next 4 or 5 minutes reinforcing this point. He's told us the point, and then he's going to show us again and again. And this is the most time he spends on a single point and the most number of demonstrations for a single idea. And it's an interesting question why he does these 6 or 7 demonstrations and spends so much time. I mean, is it because he's a showman and he just has lots of things that are really interesting to show? Or is it because he's a teacher that knows that this idea, that gases having weight, having matter, is counterintuitive notion for scientists, for students rather, that are new to science?
And we have evidence of this today. There's a classic question that's given especially to middle schoolers, for example, in which they're shown 3 thin, hollow metallic spheres, one with a vacuum, one filled with helium, and one with air, floating in water. And they're asked which one would float the highest. And of course, if we go by weight, the one with the vacuum should float the highest. But almost universally, the students pick the one with helium because they know that helium floats.
So it took me a while to find the balance that's in this image here. We could have used a modern one, with a digital readout, but this is very visual. And I found one at our campus surplus. It's where they junk old equipment. And it was pretty beat up, and I actually had to paint the bottom, the gray part, so it looked good. So now he's going to show us the consequence of air having weight. And we think of a finger as sticking, by suction, but really it's the weight of the air. And notice this is one of several times that he takes us something that we describe in commonplace language, but in an accurate way, and he reinterprets it with a scientific view.
And what was really nice is that he started off by talking about the fact that air does have weight, and he showed us this. He had the 2 containers, both of them filled with air, and he put more air in one, and he showed how air actually does have weight. Well, the atmosphere, of course, is made up of air, and if air has weight, then the atmosphere has weight. And so instead of talking about suction, which kind of implies that a vacuum has this force that's driving inward, he talks about the weight of the air actually pushing down.
That was done entirely by the weight of the air pressing on it, and you can easily understand how that is. So what's kind of interesting to me about this demonstration, just looking at Faraday's lecture technique, is this is the only time that he's used a schematic demonstration. So he didn't have something actual to show us, and so he's using this just kind of illustrative way with a set of blocks to show us what's going on.
And this was something similar to what we did, but we had the advantage of having something like PowerPoint, and so we were able to show a lot of graphics, and he wasn't able to do that.
This is a very famous experiment. It was done in the 17th century by a German scientist named Otto von Guericke, who lived in Magdeburg, and he used very large spheres to do this. You can actually see it in the Deutsches Museum in Munich, and you can buy these spheres just to do this, like we bought them from some chemistry supply house.
So it's important to point out here that it looks as though the pressure is increasing by the gauge, but that's actually the amount below atmospheric pressure that it's decreasing.
You can see here already how hard these are to pull apart. In the case of the giant spheres of von Guericke in Magdeburg, the hemispheres were 2 feet in diameter. It's about 15 pounds per square inch pressure, and that means you need 60 or 70,000 pounds to pull them apart, and so they used 16 horses and were unable to pull them apart at all. So Faraday here uses a suction cup, and as we discussed already, suction isn't the right word. What's really holding this on is the pressure that is pressing on the suction cup. I was a little surprised to see him mention suction cups. I didn't think they'd have them at the time, but I learned since then that the suction cups have been around since at least the 3rd century BC. They were made out of gourds and used to suction bad blood from internal organs to race it to the surface. And Faraday actually called them suckers.
And it's interesting too. It's another example of him using something that people would be familiar with and kind of relate this to the lectures.
This is another thing I was surprised to see in his lectures as a pop gun, but I've gone back to the original language, and what he says is that you can make a pop gun out of a quill or a tube or anything of that kind, where we take a slice of potato, for instance, or an apple, and take that tube and cut out a pellet, as I have done, and push it to one end. So kids at that time would make their own pellet guns.
And we've mentioned this a lot, but it bears repeating. Faraday was a really good showman. And in this case, he actually lowers his expectations here. He tells everyone he's going to blow an egg from one cup to the other. And then he says, well, I may not be successful because I've been talking too much. And of course, he is successful. And he mentions that it's a fact that the air has weight, so it's made of matter, and if it's made of matter, it can actually, when it comes in contact with something, move that object. Now, in this particular case, we have to admit we cheated just a little bit. Faraday mentions that if you want to do this, you should hard boil the egg. We actually used a hollow plastic egg to do this because it was lighter and because we didn't want to go through a lot of eggs.
So now he turns his attention from the weight of the air to the elasticity of the air, and that's what he's showing with a pop gun and how it works. And he's going to show that elasticity in the next demonstration also, and reminds us that this is how we can get a lot of air into those bottles. It's actually, first of all, it's interesting that this is the first time he mentions a mechanical property, I believe, and I don't think he mentions one again. And then it's a little odd about why he spends this time on elasticity of air, because it doesn't really come back to the candle, which we're going to get back to here in a little bit by the end of this lecture, and more so in lecture 5 for a bit. So I don't know. He wants to do it maybe for completeness?
Yeah, I think, going back, if you were wondering how did he fill up those bottles or how did that pop gun work, he's got to use the elasticity or the compressibility of air to explain it. Now this demonstration, though, is a really nice one. When we talked about how Faraday is kind of the godfather of chemistry demonstrations, we still use this one today. And we actually not only use this with balloons, we'll use it with marshmallows or with shaving cream, anything, of course, that's filled essentially with air. And it's always a crowd pleaser.
I remember filming this, that motor is actually extremely loud. And in the soundtrack, I actually lowered the sound quite a bit. And Alex Black, who created this series with us, kept asking me to make it lower and lower and quieter until it just is that kind of hum that you hear now. And now, at long last, Faraday returns to the candle.
So he has a really nice setup here. He has this open system on the top and the bottom that allows the candle to burn. Takes a little bit of time to remind us one of the products of the candle is water, and he shows us that we can see the water vapor collecting there at the top. But what he's really interested in is finding other products of the candle, something we, as he said, we have not yet examined. And this is also a really good demonstration, like he's done before, where he makes the invisible visible, something that he'll show us the effect of something. Now, when he holds this match up, he shows that it flickers a little bit. It's not mechanically blowing this out. And he's going to mention this in lecture 5 when he uses his breath to do this. And we can see here that the flame goes out. He makes an assumption here that we might think it's because of nitrogen. He's already shown us that nitrogen doesn't support combustion, but he's gonna anticipate, as he says, a little bit. He knows this isn't nitrogen, but something else that doesn't support combustion, and so he's gonna take the next few minutes to show a series of tests about what this gas actually is.
So what he's going to do here is he's going to take the gas that's coming from the candle, and he's going to mix it with lime water. And lime water is just calcium oxide dissolved in water. And we know today that when CO2 mixes with calcium oxide, that calcium carbonate precipitates, and that's how come you get the cloudy color.
And you just called that CO2. I mean, it's almost impossible for us nowadays to not use the phrase carbon dioxide or CO2 as we're talking about this, because we know what this is. But true to form, Faraday doesn't give this gas a name until he's actually tested for it and shown us. So again, show first and then tell. And of course, Faraday never really called this carbon dioxide. He used the phrase of the time, carbonic acid. It's kind of obvious to us now that carbon dioxide would be made of carbon and oxygen. Now, notice though what Faraday does. He does a really good job, scientific method approach to this. He has a test, the test gas, the gas coming off from the candle, and then he has his control using air. And remember, he kind of made this assumption that we might think that nitrogen was reacting with this. Well, of course, he's already shown us that air is mostly nitrogen. So if the air doesn't react with the lime water, then obviously nitrogen doesn't react with the lime water. So this gas, it's not water, it's not oxygen, it's not nitrogen, so it must be something new. Now, in this next segment, we did have to change the language a bit based on kind of Faraday's interpretation of what was going on.
So the part that's coming up, we had to change the lecture just a little bit. You may recall earlier that we mentioned that, well, Faraday would know the existence of atoms. He wouldn't necessarily understand their arrangement in molecules. And he's talking here about how you can get carbon dioxide, CO2, from chalks and corals and other things. And his language kind of implies that the gas is trapped in there and then physically released, and really it's a chemical change. You're actually producing the CO2, which he's going to do here in the next section, actually.
But it's nice here, though, to see this kind of, again, this universality coming along, where Faraday mentions that the carbon dioxide is coming from the candle, but it also comes from corals, from shells. He's going to see that, tell us that it comes from our breath, also comes here from marble.
So let's listen to how Faraday describes this piece of marble. Here is a substance, marble, a very beautiful and superior marble, and if I put that piece into the jar, a great boiling apparently goes on. So I don't know if ours is a superior piece of marble, but I will tell you it comes from Lowe's, the hardware store. And what it is, it's the threshold, I believe, for a door. And you can buy these long pieces of marble and break it off. So you can do this experiment at home if you want, or in the classroom.
So Faraday had just mentioned that when he added the marble to the hydrochloric acid, that a great boiling apparently goes on. And it looked as though it was boiling. We saw the bubbles. Just like with the electrolysis, when he took the water apart to make hydrogen and oxygen, he mentioned you might think that this is boiling. Because again, it looks as though it is. But he tells us that it's not steam that's coming up, but it's another gas, and it's a chemical change, not a physical change.
So now here Faraday uses chalk as a source of calcium carbonate, and if you're going to try this at home or in the classroom, you might be aware that not all chalk today contains calcium carbonate. Some of it's calcium sulfate, so you want to be careful what you get.
So here's another example of unity that Faraday always likes, that the water is water idea. A candle can produce carbon dioxide, the marble can produce carbon dioxide, and the chalk can produce carbon dioxide. And this carbon dioxide is all the same. It doesn't matter from which source it came.
So over the next few minutes, he's going to do a couple of tests to detect carbon dioxide. And the reason he puts these at the end of this lecture and reminds us of these is that in the next lecture, he's going to show that when we exhale, it contains carbon dioxide.
Now, Faraday is following a familiar pattern here as he has in the other lectures. He isolates the substance, the carbon dioxide, collects a large quantity of it, and then he begins to figure out its nature. He shows us that it doesn't support combustion. He lets us know that we collect it over water, so it doesn't dissolve in water. He lets us know as well that it will react with lime water to turn cloudy. And then he talks about one of the first properties he talks about is that it's a weighty gas, that it's heavier than nitrogen and oxygen that are in the air.
And notice here in this table that he's comparing it to the gases he already isolated in this lecture, so that you should be familiar with them. And while he tells us this, he has a very visual way to show this density later in the lecture. Now, here we produce CO2 from a dry ice. Of course, Faraday didn't do that. He probably produced it from the marble. But if you're a teacher and you want to do this, you can usually get dry ice at a place like a butcher shop, right?
Yes. And this is another great one in which Faraday makes the invisible visible, and he pours the carbon dioxide, which of course is counterintuitive for a few reasons. One, we don't think anything is in that flask, and two, as we've mentioned before, a lot of people don't think gases have weight at all. But you can use this actually to grab the attention of kids. They think of it as magic at first, and then we can explain the science behind it afterwards.
This is a beautiful demonstration by Michael Faraday, maybe Faraday at his best visually. alert viewer will note that that enclosure is what we used to cover the ice bomb when it blew up.
And this is well worth doing with kids. And even if you don't have access to dry ice, you can always use an old aquarium and just use baking soda and vinegar to make the carbon dioxide.
So that completes our commentary for Lecture 4, and when we meet again and discuss Lecture 5, he's going to discuss respiration and show how what happens at a candle is similar to what happens in respiration. So I'm Bill Hammack.
And I'm Don DeCoste.
And thanks for listening.